TON 618 is often described as one of the most massive black holes ever known. Estimates suggest a mass roughly 60 to 70 billion times that of the Sun. The number sounds precise. Yet there is a quiet contradiction at its core. No one has ever seen this black hole directly, and no one can measure its mass the way we would weigh an ordinary object. What we actually observe is not the black hole itself. We see only the light from its surroundings. We see radiation spectra. We see distant traces left behind in space. From these indirect signals, science begins to construct numbers. Every measurement relies on models. Every conclusion carries uncertainty. This leads to the central question of this video. How do we truly know that TON 618 is that massive? And how reliable are the numbers we place our trust in? Before we talk about the mass of TON 618, we have to begin with a different number. One that sounds less dramatic, but matters far more. Distance. In astronomy, distance is not a secondary detail. It is the foundation of every other measurement. If the distance is wrong, everything built on top of it shifts as well. With TON 618, there is no direct way to measure distance. No physical ruler, no radar signal, no predefined marker placed in deep space. Instead, we rely on light, more specifically, on how that light has been stretched as it travels through an expanding universe. This effect is known as redshift. When a light source is extremely distant, its wavelengths are stretched. Familiar spectral lines slide toward the red end of the spectrum. For TON 618, spectral lines reveal a redshift of approximately 2.2. This is not a guess. It is directly measured from telescope observations. But redshift itself is not distance. It only tells us how much the universe has expanded since the light left its source. To turn redshift into distance, we need a model of the universe. More precisely, assumptions about expansion rate, matter content, and dark energy. Using current cosmological models, light from TON 618 has traveled for about 10.8 billion years to reach Earth. We are seeing it as it existed when the universe was much younger. But light travel time is not the same as present-day distance. During that journey, space itself continued to expand. When this expansion is accounted for, the present-day cosmological distance, known as the co-moving distance, reaches roughly 18 billion light-years. This number defies everyday intuition. It exceeds the age of the universe in a simple sense. Yet in cosmology, it is entirely possible. At this distance, every other measurement becomes fragile. Observed brightness depends directly on how far away the source truly is. The inferred size of emitting regions also depends on distance. A small error in distance becomes a large error in physical scale. And finally, mass. Most methods for estimating black hole mass begin with luminosity and size. Both are distance dependent. This means the mass of TON 618 is not an independent number. It is the final result of a chain of reasoning, with distance as the first link. If the distance is off by 10%, inferred luminosity shifts by more than that. Emission region sizes change, and mass can drift by tens of percent. This is not a failure of any single measurement. It is a natural limitation of observing the universe at extreme scales. When we say TON 618 is tens of billions of light-years away, we are not just describing its location. We are defining the certainty of every number that follows. And so, Before asking how massive it is, a more fundamental question emerges. How well do we truly know how far away it is? When an object lies tens of billions of light years away, the natural expectation is that it should nearly vanish from view. Light fades with distance, and the universe offers no special favor to distant sources. TON 618 behaves differently. Despite its extreme distance, it still stands out as an unmistakable source of light. This forces us to ask not about distance, but about brightness. In astronomy, brightness is viewed in two very different ways. One is apparent brightness, how bright an object appears from Earth. The other is absolute luminosity, how much energy the object actually emits. Apparent brightness is strongly shaped by distance. An extremely luminous object can appear faint if it is far enough away. A much weaker object can seem bright simply because it is close. Absolute luminosity asks a deeper question. If we could place the object at a standard distance, how bright would it truly be? When this approach is applied to TON 618, the result becomes immediately extraordinary. Estimates place its absolute luminosity at around 140 trillion times that of the Sun. This is not merely a large number. It far exceeds anything we are accustomed to when thinking about luminous objects in the universe. To grasp this, remember that the Sun alone sustains all life on Earth. Every second, it releases an enormous amount of energy. TON 618, in terms of luminosity, is equivalent to hundreds of trillions of suns operating at the same time. Not briefly, but continuously, over long periods. When converted into physical power, this corresponds to roughly 10 to the power of 40 watts. This level of energy is almost beyond comprehension. With such power output, TON 618 belongs to the class known as hyperluminous quasars. These are among the most extreme light sources ever observed. But quasars are not stars. They do not generate energy through nuclear fusion like the Sun. This leads to a deeper question. Where does that energy come from? The answer lies at the system's center. There, a supermassive black hole is consuming matter from its surroundings. As matter falls toward the black hole, it does not vanish immediately. It spirals into an accretion disk, compressed, accelerated, and heated to extreme temperatures. It is this process that releases energy, not from the black hole itself, but from the infalling matter. Remarkably, this accretion process is far more efficient than nuclear fusion. A small fraction of mass can be directly converted into energy. To produce the observed luminosity of TON 618, the rate of infalling matter must be enormous. This implies a central engine operating near physical limits. Even here, we are not measuring power directly. Luminosity is inferred from detected light and the assumed distance. If the distance changes, absolute luminosity shifts as well. A small distance error can produce a large change in inferred power. This makes luminosity a measurement that is both powerful and fragile. It lets us infer the scale of the central engine, but only within the limits of our models. Here is where TON 618 begins to break familiar astronomical intuition. An object this distant, yet this bright, cannot be an ordinary system. It forces us to accept that something far more extreme than most known phenomena is taking place at its core. And this leads directly to the next question. If the luminosity is already this immense, how massive must the system be to sustain it? When it comes to measuring the mass of a black hole, we face a simple reality. A black hole emits no light. It reflects none, and in most cases, it is completely invisible. This means every piece of information we obtain does not come from the black hole itself. It comes from its surroundings. In a quasar like TON 618, that environment is especially violent. Vast amounts of gas and matter move at extreme speeds near the central region. As this gas is heated and ionized, it emits light at very specific wavelengths. These signals appear in spectra as emission lines. In ordinary sources, these spectral lines are relatively narrow. In quasars, they become remarkably broad. The width of a spectral line is not a random detail. It directly reflects the speed of the moving gas. As gas moves faster, the Doppler shift becomes stronger. Some light is pushed toward the blue, some toward the red. The result is a spectral line stretched across a wide range of wavelengths. In the case of TON 618, these emission lines indicate gas velocities reaching thousands of kilometers per second. These are speeds unattainable in ordinary stellar systems. They appear only when the central gravitational pull is extreme. The principle here is relatively simple. The faster matter orbits a center. The more massive that center must be. We have used this principle for a long time. It explains planets orbiting the Sun. It explains stars moving within galaxies. In quasars, this principle is pushed to its limits. Instead of stars, we observe gas clouds. Instead of tens of kilometers per second, we see thousands. The metric commonly used to quantify this is known as FWHM. It describes the width of a spectral line at a specific intensity level. From the FWHM, astronomers infer characteristic gas velocities. From those velocities, they begin estimating the central gravitational force. Here, however, a crucial assumption enters the picture. The assumption that the gas motion is dominated by gravity. If the gas simply orbits the black hole in stable paths, its velocity directly reflects the central mass. But a quasar environment is not a calm system. It is chaotic, violent, influenced by many forces. Radiation pressure from intense light can push gas outward. Magnetic fields can deflect motion. Winds and outflows can generate speeds unrelated to gravity. If some of the measured velocity comes from these effects, the inferred mass will be overestimated. This makes spectral line width measurements both powerful and fragile. They are highly sensitive to mass, but also to assumptions. For TON 618, this issue becomes even more serious. We are observing one of the brightest quasars ever known. Radiation pressure here is extreme. This raises an unavoidable question. How much of the measured velocity truly comes from the black hole's gravity? And how much comes from the very light the quasar emits? We can measure spectral line widths with high precision, but translating them into mass always carries uncertainty. So when we say TON 618 has a mass of tens of billions of suns, we are describing an inference from gas motion, not a direct measurement. And this is where science moves to the next step. How to turn these velocities into a concrete mass value. To do that, astronomers need a method that links velocity, size, and gravity. This is where the virial method enters the story. After measuring the gas velocities around TON 618, science still lacks the most important quantity. Velocity alone is not mass. To move from motion to mass, we need a physical bridge, a principle that connects speed, size, and gravity. That bridge is known as the virial method. It was not invented for black holes, but originates from classical mechanics. The core idea of the virial principle is simple. In a gravity-dominated system, kinetic energy and gravitational energy maintain a stable relationship. In other words, if we know how fast matter is moving and over what size scale, we can infer the mass holding the system together. When applied to quasars, the formula is usually expressed this way. Mass is proportional to the square of the gas velocity multiplied by the size of the emitting region. The velocity, as we have seen, is inferred from spectral line widths. This part is relatively direct, though still uncertain. The size of the emitting region, however, is not. This is where the virial method becomes most indirect. We cannot directly see the emitting gas region around TON 618. It is too distant and too small on the sky. Instead, this size is inferred from the quasar's luminosity. More precisely, from a correlation between luminosity and emission region radius. This correlation is not arbitrary. It is built from nearby quasars, where light travel delays can be measured. In nearby systems, when the quasar's brightness changes, the responding emission from surrounding gas arrives with a measurable delay. From that delay, astronomers infer the physical size of the emitting region. It is one of the few ways to measure size indirectly in astronomy. Those results are then used to calibrate the relationship between luminosity and size. When applying that relationship to distant quasars like TON 618, we assume that physics at great distances behaves the same as nearby physics. It is a reasonable assumption, but not an absolute certainty. The universe at the time TON 618's light was emitted was very different from today. Environment, density, and physical conditions may all have differed. If the luminosity-size relationship evolves over cosmic time, the inferred size for TON 618 would be inaccurate, and if the size is wrong, the mass inferred from the virial formula will be wrong as well. This highlights a key feature of the virial method. It does not measure mass directly. It infers mass through a chain of reasonable assumptions. Each link in that chain is grounded in observation, but each also carries uncertainty. For typical quasars, this method works reasonably well. The results often agree with independent measurements, but TON 618 is not a typical quasar. It sits at the extreme edge of every familiar distribution. When we push the virial method to such extremes, small uncertainties can amplify into large discrepancies. This is why mass estimates for TON 618 never produce a single definitive number. They always come with a range. It is important to understand that the virial method is not wrong. It is the best tool we currently have. It reflects the true nature of observational science. We do not measure directly. We infer from what the universe allows us to see. So, when we talk about the mass of TON 618, we are not only talking about a black hole, we are also talking about the power and limits of human models. And this leads to a reflective question. Are we truly measuring the black hole, or are we measuring our own assumptions about the universe? After understanding how velocity is measured and how the virial method turns velocity into mass, we can return to the central question. Where does the mass number of TON 618 actually come from? In reality, there is no single measurement producing one fixed value. Instead, there are multiple independent studies, each using different spectral data The result is a range of values. Some studies place the mass around 40 billion times the Sun. Others push it to 60 or even 70 billion. These differences are not random errors. They reflect different choices in measurement and interpretation. One key factor lies in the type of spectral line used. In quasars, not all emission lines originate from the same region. Some lines, such as C4, originate from gas very close to the center. These regions are strongly affected by winds and radiation pressure. Other lines, such as MG2, come from regions slightly farther out. They are generally more stable and less disturbed. When different lines are used, the inferred velocities differ. And when velocity changes, the inferred mass changes with its square. This means that a relatively small difference in velocity can lead to a very large difference in final mass. Another factor is the geometry of the emitting gas region. The virial method often assumes the gas is symmetrically distributed around the black hole. In reality, the structure can be far more complex. The gas may be flattened, elongated, or dominated by flows in preferred directions. If the true geometry differs from the assumption, the inferred mass will be biased, not because the data is wrong, but because the model is incomplete. This is why scientific papers rarely present a single definitive mass for TON 618. Instead, they provide a range. That range reflects the confidence level of the method. It shows where science is certain and where it remains unsure. What is striking is that even at the lowest end of this range, TON 618 remains an extreme black hole. A mass of around 40 billion suns still far exceeds most known supermassive black holes. So the question is not only which number is correct, it is also what standard we use to call something a monster. If TON 618 is lighter than the highest estimates, does that make it any less extraordinary? In the context of the entire known black hole population, the answer is likely no. Even at the lower end, TON 618 still sits at the edge of what we have ever observed. More importantly, these numbers reveal the limits of measurement. They show that at the extremes of the universe, precision becomes a challenge. TON 618 is not just a large black hole. It is a test of the very methods we use to understand the universe. And from here, a deeper question begins to form. If the mass is already this large, what does its physical size look like? When we speak of masses tens of billions of times that of the Sun, we tend to think in terms of weight. But for a black hole, mass immediately leads to another concept: size. For a black hole, size is not a physical diameter in the usual sense. It is defined by the Schwarzschild radius. The Schwarzschild radius marks the boundary beyond which nothing can escape. Not even light. This is the event horizon. Crucially, this radius scales linearly with mass. Double the mass, and the radius doubles as well. As the mass of TON 618 rises to tens of billions of suns, its Schwarzschild radius becomes extraordinary in scale. Estimates place the event horizon radius of TON 618 at roughly 1,200 to 1,300 astronomical units. To put this in context, 1 astronomical unit is the average distance between Earth and the Sun. This means the radius of TON 618 alone exceeds the scale of our entire familiar solar system. Yet, even astronomical units quickly lose their intuitive meaning. At this scale, another comparison becomes more useful: light travel time. Light travels at the fastest speed allowed by the universe. Light travel time, therefore, becomes a natural ruler for cosmic size. Given the radius of TON 618, light would take roughly 6 to 7 days to travel from the center to the event horizon. This means the radius alone is measured in light days, not kilometers. If we consider the full black hole shadow, the region where space-time is so warped that light is trapped, the light crossing time stretches to about 2 weeks. This is a scale where everyday physical intuition begins to fail. We are accustomed to measuring objects in meters, kilometers, or even Earth radii. Here, those units become nearly meaningless. TON 618 is not a tiny point with infinite gravity. It is a space-time structure spread across an enormous region. This often contradicts popular images of black holes. They are not tiny pinholes devouring everything nearby. For supermassive black holes like TON 618, gravity at the event horizon can even be relatively gentle. What makes them extraordinary is not intensity at a point, but the vast region of space they dominate. When an object's size is measured in light days, concepts of proximity and distance must be rethought. A hypothetical light speed probe would take days just to cross from one edge to the other. At this scale, space and time are no longer passive backgrounds. They are deeply warped by mass. That curvature shapes every motion, every orbit, and every measurement we make. When we say TON 618 has this size, we are not just stating a number. We are admitting that ordinary geometric intuition no longer suffices. At this scale, a fundamental problem begins to come into focus. When size reaches this extreme, how much of our familiar physical thinking still applies? And this is precisely the context needed to move to the next measure: the physical limits of luminosity and mass. When an object emits light, it does more than illuminate its surroundings. That light carries momentum, and that momentum creates pressure. In most ordinary situations, radiation pressure is negligible, but in extremely luminous systems, it becomes a real force. For accreting black holes, this leads to an important physical limit. If the light output becomes too strong, radiation pressure pushes matter outward, preventing further infall. This limit is known as the Eddington limit. It represents the maximum luminosity an object can sustain while remaining in equilibrium. Below this limit, gravity dominates. Matter continues to fall inward. Above it, light begins to push back against its own energy source. Crucially, the Eddington limit is not a single fixed number. It depends directly on mass. The more massive an object is, the stronger its gravity, and the higher the luminosity it can tolerate before radiation pressure takes over. With a mass of tens of billions of suns, the Eddington limit of TON 618 is extraordinarily high. In theory, this allows it to emit enormous amounts of energy while maintaining stable accretion. Yet, when the observed luminosity is compared to the inferred Eddington limit, something striking emerges. The luminosity of TON 618 does not greatly exceed this limit. It approaches it closely. This places TON 618 inches, a special regime. It appears to be operating near the physical ceiling allowed by theory. At this scale, a deeper problem begins to emerge. There are two ways to interpret this situation. The first is that TON 618 is genuinely accreting matter at the edge of physical limits. In this scenario, the system is extreme yet stable. Every process operates at the highest efficiency nature allows. But there is a second, more cautious interpretation. The luminosity, or the mass we infer, may not be entirely accurate. If the true mass is lower than estimated, the Eddington limit would also be lower. In that case, the observed luminosity may already exceed it. Conversely, if luminosity is overestimated due to distance or modeling, TON 618 may not be as close to the limit as it appears. This shows that the Eddington limit is not just a physical checkpoint. It is a test of the entire chain of inference leading up to it. When an object repeatedly presses against a theoretical ceiling, two possibilities exist. Either it is a genuine extreme outlier, or our models are being pushed beyond their comfortable range. With TON 618, neither possibility can yet be ruled out. This makes the Eddington limit one of the most subtle measures. It is both a physical law and a mirror reflecting the reliability of our measurements. And it is precisely this ambiguity that makes TON 618 special. It challenges not only physical limits, but also how we interpret data. When a system operates near a theoretical ceiling, every small uncertainty becomes significant. From here, a final uncertainty in the chain of measurement begins to take shape. Is TON 618 a lone exception, or simply the most visible example of a broader class? Up to this point, we have talked extensively about numbers, mass, luminosity, Caesar. But numbers, on their own, are difficult to feel. To truly grasp how unusual TON 618 is, we need to place it next to something familiar. Comparison is one of the most powerful tools for breaking intuition. Let us begin with the black hole we know best, the one at the center of the Milky Way. This black hole has a mass of roughly 4 million suns. It is massive enough to control the motion of stars in the galactic core. TON 618, by comparison, is about 15,000 times more massive. This is not a difference of degree. It is a difference of kind. If we place these two black holes side by side in mass terms, the Milky Way's central black hole nearly vanishes from the scale. Yet this comparison still does not reach the true extreme. There is another comparison that nearly collapses intuition. Comparing with an entire galaxy, a spiral galaxy like the Milky Way contains hundreds of billions of stars. Its total stellar mass is enormous. Estimates suggest that the mass of TON 618 may be comparable to, or even exceed, the total stellar mass of the Milky Way. This does not mean TON 618 outweighs the entire galaxy in every sense, but it reveals how extreme the number truly is. A single object, confined to a region smaller than a stellar system, carrying the mass of hundreds of billions of stars. Here, familiar astronomical relationships begin to break apart. We are accustomed to central black holes making up only a small fraction of a galaxy's mass. We are accustomed to correlations between black hole mass and stellar motion, between black holes and galactic structure. TON 618 does not sit comfortably within these relationships. It stands at the edge, or even beyond. This shows that it is not simply a large black hole. It is an extreme outlier. An outlier large enough to force us to ask whether familiar relationships apply at all scales. Perhaps TON 618 formed under extraordinarily rare conditions. Or perhaps it represents a class of objects we are only beginning to glimpse. If TON 618 exists, probability suggests it is not alone. There may be similar, or even larger, black holes lying farther away, fainter, and harder to measure. We may see TON 618 only because it happens to be luminous enough to reveal itself. This turns TON 618 into an observational milestone, not because it is definitively the largest, but because it sits at the edge where our measurements still function. From here, a broader uncertainty begins to open. Are we seeing only the visible tip of an undiscovered population? When an object breaks intuition this thoroughly, it speaks not only about itself, it speaks about the limits of how we observe the universe. And that is the natural bridge toward the conclusion. When we look back at the entire journey, one point needs to be stated clearly. TON 618 has never been weighed. No instrument has ever reached it. No direct measurement has ever touched the black hole itself. What we have are numbers. Each number comes from an indirect measurement. Each measurement relies on a model. Distance is inferred from cosmic expansion. Luminosity is calculated from detected light and foundational assumptions. Gas velocity is read from spectral lines. Mass is inferred from physical relationships calibrated elsewhere. Each step in that chain is reasonable. Each step is grounded in rigorous science, but none of them are absolute. And what is striking is that even when we push every uncertainty to its lowest possible level, the conclusion does not fundamentally change. TON 618 still sits at the edge of what physics allows. Whether it is 40, 60, or 70 billion suns, it remains an extreme outlier. Here, the core message becomes clear. TON 618 does not only challenge our idea of size, it challenges the very limits of human measurement. It shows that at the largest scales of the universe, certainty becomes a luxury. We do not lose understanding, but we must accept uncertainty as part of that understanding. TON 618, in this sense, is not just a black hole. It is a mirror reflecting the boundary between what we can measure and what we can only infer. And from here, one final question quietly emerges. If a black hole can be so large that we know it only through uncertainty and models, then the true boundary of the universe may not lie only out there. It may lie at the very limits of what we are able to measure. And that question remains open. If you would like to continue exploring the limits of the universe like this, consider subscribing so you do not miss the journeys ahead.